Hello, everyone, and welcome back to another episode of Solidity Fridays. Today, I'm joined by Stent, and we'll be looking at the powers of Tau, which is a setup ceremony for zero-knowledge proofs, particularly snarks. If you haven't got an idea of what a snark is, maybe I would suggest watching our zero-knowledge cryptography workshop video on Solidity Fridays, where we explain the different types of zero-knowledge proofs and what they entail. Hey, Stent, thanks for joining me today.
Hey Zia, how are you doing?
Yeah, very well, thanks. And yourself?
Yeah, good, thank you. Thanks for having me again.
Yeah, nice.
Just couldn't get enough here.
Yeah, no, I definitely can't. Especially now that I know you're interested in zero knowledge, maybe it could be a bit more of an occurrence on the show. I have a strong interest in zero knowledge, so it would be cool to do more episodes on it.
Yeah, man, I'm psyched. Do you want to explain a little bit about ZKPs?
Yeah, sure. So there are many different types of zero knowledge arguments and proofs, but there are two main types. The first one is an interactive zero knowledge proof, where the prover and the verifier interact several times, and then each time the verifier challenges the prover to see if they can believe them. Then you get something called a non-interactive zero knowledge proof, which is kind of what we'll be looking at today. And the interaction between the prover and verifier is simulated by the prover before the proof is created. And that simulation is called a setup ceremony. And that you get different types of setup ceremonies. Particularly, we're going to look at a trusted setup ceremony, and then we'll look into what that means in a bit.
Cool. Also, maybe a good thing to say is like an example of a non-interactive proof is a snark, also a stark, and we're going to particularly be looking at snarks today because starks don't have a setup ceremony, which is an advantage for them because setup ceremonies are seen as a bad thing. The common reference string being the thing that the ceremony creates. That thing is actually called toxic waste sometimes because it really is a big downside of ZKPs, well, particularly snarks.
We'll see why it's called that later.
Yeah. I actually don't know. I'd love to know actually why it's called toxic waste.
Well, it's because it's data that you're creating just to destroy. It's wasteful.
Okay.
I think that's why they call it toxic waste.
Okay. Yeah, and Starks don't have that problem, but they have other trade-offs that you have to make as in comparison with a snark. Like, for example, the size of the proof is not constant like a snark. It grows with the size of the computation. And the verification time also is not constant like a snark. It grows too with the size of the computation. So yeah, there's a couple trade-offs that you have to make, and there's definitely times when you would rather use a snark than a stark, like particularly on a blockchain where size and computation time, verification time cost many monies. Yeah, so anyway.
Yeah, they matter a lot. Exactly. Sorry, would you mind actually going to the next slide?
Sure thing.
We mentioned something called a common reference string, and that's just a way for a prover and a verifier to know that they're looking at the same statement, and the statement is what we're proving. I just wanted to mention that. Cool. So the particular type of implementation of powers of Tau that we will be looking at today is done by A16Z in this repository. And we find it very elegant, and it's in Solidity, so it works.
Do you know what A16Z stands for? What word starts with A and a Z and has 16 characters? No, I have no idea.
I'll look into it.
Cool. Yeah, okay, so let's talk quickly about, before we dive into the code, maybe it's good to go over a little bit of theory. So the first thing is just to maybe explain a bit more the common reference string. So this over here is the original 2016 Grath paper that introduced the snark, or was the first one to describe a snark. As far as I understand, it was the first one. And in this paper, literally right here is the definition of tau, just a random Greek letter. It could have been anything. There's no particular resemblance to 2 pi, which is also known as tau, which kind of reminded me
This
of
is
the
a funny
KCD
comic.
comic. Yeah, I love it. It's great. Man. Pal. So good. Okay. It has no relation to that. It's just a random letter, but it's stuck now. And it's kind of cool. I don't know. It's a kind of cool sounding ceremony, powers of Tau. So anyway, this thing is a vector of five elements. Well, 5-dimensional vector. Each of these things being inside of the field. They're all elements in the field, and these things are used to generate a bunch of stuff that is required to have ZK snark. So basically, in the setup, you create this common reference string, and I think actually this is the entirety of it right here. I'm not 100% sure, but it's a really long thing. I'm not sure if this is the correct thing, but anyway, it's very long. Like, there's a lot of data in there, and both the provers and the verifiers use that to create and verify proofs, and it is specific to a single computation. So if you want to set up a different ZK snark, like suppose you're trying to prove the EVM, so like a ZK EVM, you need to do a setup ceremony. If you do an update to that computation, like, I don't know, you add logs or you add another EIP or something like this, then you need to redo the entire setup ceremony. That's the idea.
So
anyway,
it's not universal. A universal setup is set up once and then it's valid for everything. This isn't a case of that. Maybe that we could look at in a different episode.
Yeah.
And sorry, just important to mention that these numbers, the elements in the vector, are generally randomized so that people can't guess them, because if someone knew them, they could falsify this proof. So it's important that only the system knows what these numbers are and that they're random, and that both the prover and the verifier themselves don't even know what these numbers are or these elements.
Yeah, basically, if you have these elements, then you can fake proofs, and no one can tell if a proof is fake or not, right? So someone could have been faking proofs for as long as they want, no one would be the wiser. So it's incredibly important that the person or the computer or the entity that creates the ZK snark setup, does the whole thing, actually deletes this data. And then you also want the data to be random so that it can't just be guessed. You want the data to be deleted so it can't be like copied or whatever, and you want the data to be random so it can't be guessed. And it's people go to like some pretty extreme lengths to make sure that those things happen. Like this, I think, is the funniest one that I found. Basically, in the setup of one of the Zcash versions, I'm not sure which ones. I think a pretty recent one actually. There was these two dudes who took this thing you see the thing in the plastic on the table there, took this piece from Chernobyl, so it's quite highly radioactive, and they got the randomness by plugging putting this to a Geiger counter and getting that data on the computer. That was the source of the randomness. And then to make sure that nobody else knew the data on the computer, the random data that they generated, they even went into an airplane, far away from any other computers. They circled around for a bit to make sure there were no drones following them, and then did the whole setup inside of the air there. I mean, just really quite ridiculous. But this stuff kind of needs to be done. Maybe not quite like as ridiculous as this, but it needs to be done in a verifiably secure manner. And the powers of Tau is one way to do that, where you can have many, many, many people involved in this setup, not just one person. Like in the original Grath paper, this requires just one person to set these up. You rather have many, many people involved in the setup, and only one of those many people needs to be an honest actor, i.e. just delete the data and not keep it, in order for the entire setup to be a success. And also, if people wanted to be able to fake proofs, they would need to have everyone's secret data. So basically, everyone involved would have to get together and then combine their secret data to get the like resulting secret data, and then they could fake proof. So
I see.
it's a way of
It's more secure by being a multi-party computation, and the more actors you add into the setup ceremony, the more secure it becomes, because the more data you would need to replicate to falsify the proof.
Exactly. And the original, like, so I think this, I don't know if this particular paper came with an MPC, but MPCs were just like were used pretty much from the beginning, like especially in Zcash setup. But they weren't powers of tau ceremony. So it was a multi-party computation, meaning there were lots of people involved, and it has having the similar property that I just mentioned before, where only one person needs to be honest and everybody needs to get together in order to be able to fake proofs. But there were very limited number of people who were involved, and the amount of computation and upload and download sizes were massive. I think on the order of tens of gigabytes, like to download and upload. So you download some data, compute it, and then upload that. So it wasn't very much accessible to the general public. It was like very select few people who were chosen, and then they would do it in different places around the world, and they would do it in public, so that people could verify that they destroyed the data or whatever. But anyway, then Powers of Tau came around, and this is 1 year later, so like not too much later than the original graph paper, and it is a much more efficient way to do a multi-party computation to construct the resulting tau, and it basically also has this nice property which the previous MPCs did not have, where any number of people can be involved. So, for example, and it's very cheap too. It's like so cheap actually that you can put it on the blockchain, which is the code that we're going to be reading in a little bit. And an example of this being performed was the Tornado Cash setup, I think, also in 2017, where more than 1,000 people were involved, or all random people, like anyone could be involved in the setup. So. It's definitely a big step forward in terms of the setup for a snark. So that's a little bit about that. What else? The reason why it's called powers of tau. The power is there because you take powers of elements in the group, and I actually try to find. I think it's just here, like literally. So G is a generator for the group. And each J, so this step here is computed as many times as you want by different actors. So J is an actor over here, and then basically what you do is you take powers of your generator element, and I think that's where it gets the name powers of tau. Yeah, it's weird because powers of tau is the resulting secret. So I think they were just having fun with the name. It's
almost like it should be called the Tau of Powers, because it's the resulting Tau of some powers.
Yeah,
but that doesn't roll off the tongue.
No, but that's great. Okay, cool. So something else that I wanted to go through. Well, this particular section over here of the paper, so this is where they explain the protocol. So here is our protocol, and it talks a little bit about the circuit, the snark circuit, and then it just says that there is this other actor called the protocol coordinator, which needs to be part of the setup. And this is not a trusted, or it doesn't need to be a trusted actor. It's just a different type of actor. You have the n number of like random actors, n being any arbitrary large number. And then you have this protocol coordinator, which is the other type of actor in this setup. And then talks a bit about NPC there. And then this is literally like the description of the algorithm over here. The phase structure. This is the verification that happens, which has to happen at each point. So after each actor has like added to the powers of tau ceremony, added their little piece, then a verification needs to be done. And okay, this is just proving that it is secure. So it's just this little section over here, which is showing the algorithm. I think we will come back to this in a little bit later when we want to see what the code is doing. But another thing that's here's a nice little diagram about how the powers of Tau ceremony works. It's really simple, like it's an oversimplification, but I don't know, it's nice to have in one's mind, like as a picture. So, one person does something and the coordinator adds to that information, and then the verifier verifies it. The verifier could be whatever, it doesn't need to be an actor, it could literally just be some code on the blockchain, as we will see shortly. And then it goes over to contributor 2, et cetera, et cetera. And each one of these is a round, although I think I'm saying the wrong word there because the original paper called rounds something else. Let me actually find that quickly. And actually, while we're on this particular topic, I think, I'm not so sure about this, like T, correct me if I'm wrong, but I think the MPC is partly powers of Tau and then partly some other computation. And the powers of Tau is universal. So you can do that for any SNARK. Any SNARK can use the results. So any SNARK setup can use the results of a single powers of Tau ceremony, but then also needs to do some stuff on top of that. I think that's
so,
correct.
Yes.
Yeah.
Is it that MMORPG?
That's so this whole paper is that thing.
Oh, I see. So it's that plus
Yeah.
an extra set of extra round, almost like a. Oh, here we go. Yeah.
Yeah. So this is the paper, and it says round 1, which is termed here the powers of Tau, and there's also no mention of the circuit. So where there's no mention of the circuit here. These are just elements in the field, blah blah blah. Has nothing to do with the circuit here. This has nothing to do with the circuit. I don't know what this algorithm does, to be honest, but look, I mean, the inputs have nothing to do with the circuit. Wait, I wonder if we can actually just quickly see what that does.
And if you don't know what an arithmetic circuit is, definitely watch that Zero Knowledge workshop. We explain it.
Yeah, maybe just very briefly, like a piece of code, a computation gets turned into an arithmetic circuit, which gets turned into a polynomial, and then the polynomials are where all the math is done. Like, yeah, very briefly. Hello. Okay, there we go. Here's the. Yeah, I mean, there's nothing. Man, I don't want to go down this rabbit hole. What's R? I don't think there's anything to do with the circuit in R.
No.
Yeah, no. Okay, let's go back down here. So there was that round 1, which is termed the powers of Tau, and then blah blah blah.
Then after each round, there's a verification.
Round 2. No, so the thing is, round is I think a mixed
I see.
term
So
here.
round means the powers of Tau. It has like sub steps. Let's just call them steps, maybe. In between each step, there's a verification, and then there's always a round 2, which goes along with the powers of Tau to create the setup.
Yeah, exactly. And here, what is this L and M? N is usually the power of the polynomial, and as we know, the polynomial is representative of the computation.
Not the circuit.
Yeah. Well, whichever, the circuit's turned into the polynomial, so whichever one. I'm trying to just see like some evidence for that, but I can't find it. There we go. Oh, yeah, they're right here. So they're the polynomials, right? And the polynomials are specific to the SNARK. So round 2 is the non-universal bit, and round 1, which is termed powers of Tau, is universal. So you can use it for any SNARK. And this round 1 and round 2 together is one way to produce the common reference string, which is needed for every single SNARK setup.
Yes.
But the nice thing about having this split into 2 rounds is that you can have a very secure, very long powers of Tau with thousands of people involved, right? And that is now the base of the security. Exactly, a super short round 2 that can be done by a dev team, and they can't. The security of the resulting CRS can't be broken.
Another nice thing is that you can get something, we might not look at it today, but you can get something called a perpetual powers of tau. So round 1 could be running, and then you could put different power round 2s over it. So you could, it really would be quite, here we go, yeah.
Yeah,
Okay, so they
I
call it
also
phase 1 and
wasn't.
phase 2.
Yeah.
My understanding is that this powers of tau ceremony continues perpetually, and then you can do different phase 2s over it.
Yeah, exactly. And I think
So it's really quick.
I think, yeah, I'm not sure that it's different from the powers of Tau, perpetual powers of Tau. I think it's just different ways of saying the same thing. So, and also this guy is also abusing the words here. Round 1 or round in this particular article is not the same
It's a
as
step or a
round
phase,
in.
yeah. He swapped
Yeah,
round and
exactly.
phase, yeah.
Yeah, exactly. So anyway, this chain at the top here is the powers of Tau, which is what they were talking about here in the
Yes,
paper
all of
in
that,
round 1.
and what we'll look at in the code.
Yeah, and it's kind of like a chain, So each individual actor can add on the top of this chain whatever they want, and then when you want to create your common reference string for your ZK snark, then you can branch off at any point in the chain and do the second part, which is round 2 in the paper and phase 2 in this article. Cool. Okay, so I think that's enough theories for now. Oh, this is also quite interesting. I found this little diagram, which is not as maths heavy, but also just kind of has a bit of a visual element to it. So this is also swapped phase and rounds. So no, I lie. This is using the correct words. Yeah, no, this is using the correct words. And I think in this case, it's actually an extension of the powers of Tau, because you don't have to have player 2 and player 3. I think you just need player 1. And then in the second phase, you can have player 2, third phase, player 3. So I'm not 100% sure why they have 3 players in each phase here. But anyway, so M is, what is M? Oh, M is just a sign here. So you have this, like, you carry this thing on. G1 just being a generator for the group that everyone agrees upon. And then each person picks some random element in the field, adds that onto the running computation, and then the coordinator does some things as well. And that's the final phase. So that's how a single phase is done. And then the next phase can happen, and you can have as many phases as you want. But what's also interesting here is this phase has the polynomial inside of it. So, I'm actually not too sure what's happening here. Why has that got the polynomial? I don't know. This one confuses me a little bit. But anyway, maybe we jump into the code. I think snarks are confusing for many people, so it's fine even if we're confused.
And the code also in the README explains a bit about a trusted setup ceremony, but now we know what they are.
Yeah, I mean, they don't give a lot of information here, but okay, yeah, it's very small actually. The code, it's like so here's the code base. So there's contracts.
What does that ASCII say?
It said, sorry, it's all like mushed onto a different line now. I'll open it just now. But basically it's literally just this KZG smart contract. Says KZG POT ceremony.
Okay, nice. Thank you.
Cool. So the first thing we see is this funny thing. FR. What on earth is that big number? Well, if we have a look at where this thing is used. Oh wait, maybe before we dig into that, let's just have a quick squiz at the function. So constructor, this is the important function, this part update, which can be called by anyone. And it turns out this is the only function. This is it. This part update is the only function. The rest of these functions are actually used by that part update. So they're public, they don't need to be. They could have been private. This is literally the only function. This tiny little guy over here. That's it. Cool. So
I wonder why they made them public then. Maybe so that you can use parts of them in your own powers of Tau implementation.
Yeah, maybe. Not 100% sure. what was I going to say? Oh yeah, and this is called by anyone. So this can be called by whoever, and they can just add to the ever-growing chain of powers.
So in that way, it can have as many actors as you want. Yeah, there's no modifier there restricting any access.
Nope. And this, okay, so let's have a look at this funny. Do you want to have a guess, T? Do you know what it is?
I'm guessing it has to do with the randomness, like it.
So it's only
this is
used in
percentage.
one place. Well, it's used in one more place over there, but it's a modulo.
So okay, I see. So you get the remainder by dividing by this number?
Yeah. It's the order of the group, right? Because you have to stay with the group. Yeah. And the order of the field, sorry, not the group. Well, which is made up of two groups, but let's not get into that. This number must be prime then, or power of a prime, because this is the order of a field must always be one of those two things. And I went and looked it up when I could find one that would calculator that would take a number that big. Yeah, the one told me to get lost. I was like, please keep your number a bit smaller. So if you, here's the number right there. And if you check, it does this calculation. Oops. Oh, okay. I'm not a robot, hopefully. And then yes, P. It is a prime. You know that's a prime number. Cool. And what's very confusing, so maybe I should just clear that up now. Inside here, there is this library that's used. And this has to do with the elliptic curve. So this is all of the maths, like the addition and multiplication that is needed to be done on the elliptic curve. And the elliptic curve group, well, the elements, like how do I put this so it's not confusing? There is the
possibly
group. Yeah.
Sorry. Can you possibly just explain to the viewers what an elliptic curve is in case they don't know?
Sure. An elliptic curve kind of looks like this. Let's just get a. Let's open that guy up. So it kind of looks like this if you plot it on the Cartesian plane. And so these are examples here of elliptic curves. And the general equation for an elliptic curve is like this. And they are fascinating things. Might be like.
I know you have quite an interest in them.
Yeah, you might think that they are quite. This can't possibly be very interesting. It's like, it's such a small equation, but they are very rich and very popular in mathematics, especially in cryptography. They have really amazing properties, and secure properties. Anyway, so you can make a group using an elliptic curve, a group being this a mathematical object that is basically just like a set with an operation to combine elements. And the elliptic curve group is, so I'm not too sure what BN128 is, but it is a specific type of elliptic curve, right? What have I done? Yeah, okay. And this library on the right-hand side is all to do with that particular group. And we can see here that we have another big number, and it says P is a prime over which we form a basic field. And this is where it gets a little bit confusing, because you have the elliptic curve, which is a group, but in order to explain elements in the group, like in order to write an element of the group down, you need a field. You need to have you basically need two elements inside of a field. So you say that the elliptic curve group is over a field. So you need these two things, and it's confusing because the field itself is made up of two groups. So, but when people say groups in ZK Snark, like context, it usually means the elliptic curve group, and when people say field, it usually means the underlying field of that elliptic curve group. But what I found interesting is that I thought that was interesting. So I'm like, why are these two numbers not the same? This is like, they should be the same field anyway. So maybe you have an idea on that, T, but I am not sure what's going on there. Yeah,
I'm not too sure. I'll have to get back to you. But I've found out what a BN elliptic curve is. It's a subset of elliptical curves. BN refers to the surnames, and they are pairing-friendly curves over the field of P, which means that computations in the field FPK are feasible and have an embedding degree of K equals 12.
interesting. I didn't understand all of that, but cool. Thank you. Yeah.
But yeah, I'm not sure why the numbers are different. But
Yeah,
possibly to get two
very
different fields, but I'm not sure why you'd want two different fields.
So you can see, you know, it's used as the modular there. Oh, maybe it's important to say why you use modular. So the elements in the field, when you combine elements in the field using the operation like plus or times or whatever, you should never be able to get out of the field. You know, so if you have a finite field, which is what we use in ZK
in all ZK snarks.
Yeah, finite meaning there's just a set of finite elements in the field. If you keep adding, you know, you should never be able to get outside of those elements. So if you have a field of size 10, well, no, that would be, let me just be right here. If you have a field of size 7, because it must always be prime or power prime, then if you keep adding 1 plus 1 plus 1 plus 1 plus 1 plus 1, you're eventually going to get outside of the field. You know, you're eventually going to get to 8. And so you don't use regular plus inside of a field. You use addition modulo the size of the field, and that's why there is this modulo here. Because in regular addition on a computer, you would jump outside of the field, but we want to stay inside of the field. So you can see these modulos everywhere. That's why the modulo is there. And that's how I was able to guess that this thing over here is a prime number, because we see a modulo, I see a big number. I know that the field sizes must be big in order to have security guarantees. And so that's why I went and looked it up, and we found out that, yes, indeed, it was prime. Yeah.
I have a question for you. Where you are now, it's mod square root, not just mod.
Yeah, not sure what's happening there. Do you have any ideas?
Okay.
No. What is no? So this is interesting. Where library? Oh, using mod util. Okay, let's find mod utils quickly. Here it is. Mod square root. Let's see what this does. I don't know what this does. Okay. So it takes. I don't know. Oh, I actually found out about this the other day. I thought it was so cool. I didn't know this about Solidity, but you can basically extend any type, like base type, with a library, which is wild. So like if you say this thing over here using mod utils for UN 256, that means I can say whatever a, you know, and then I can say a dot some function in here, like that.
Oh, cool.
One, which I thought was super cool. I haven't seen that. Maybe C++ has that, I can't remember, but I haven't seen something like that in a language before. So that's really cool.
Thanks, handy tip.
Yeah, and that's what's happening here, right? So this is this item, this piece of code here is going to be a UN 256, and the reason why you can call like that on it, which you usually are not allowed to do, is because we have at the top of the library it said using this other library for this type. So if we go and read,
I've done that before by mistake, but I didn't realize I was extending the type in doing so.
Oh, cool.
Not by mistake, just like.
Yeah, just without
trying
like
to use the library function. Yeah, wow.
Yeah, cool. Okay, so we take, and A is going to be the one that has the dot. Just A is to the left of the dot. P is the one in the brackets. So let's see if Legendre. Oh my God, is this doing integrals or what is this doing? Calculates the Legendre symbol. I'm not sure what this is doing. Mod exp failed to calculate Legendre. Yeah, okay, wait. Before we jump into that, let's see what. Let's just read the.
In number theory, the Legendre symbol is a multiplicative function with values 1, -1, and 0. That is a quadratic character modulo an odd prime number p.
Could you say it again?
So the this word. The Legendre symbol is a multiplicative function with values 1, -1, and 0 only. So it's a quadratic character modulo an odd prime number p. Its value at the quadratic residue mod p is 1, and at the non-quadratic residue is -1. Its value at 0 is 0.
Okay, I can't remember what residue means, but I think we get like a rough idea. Maybe just look up what residue is. I can't remember what that is exactly. But we know the output is going to be 0, 1, or -1. So that's,
an integer
I guess,
q is called a quadratic residue modulo n if it is congruent to a perfect square modulo n. So that is if there exists an integer x such that square root of x
is an integer.
Yeah, and sorry, then it says yeah, it is an integer q mod n. So otherwise q is called a quadratic non-residue modulo n.
Okay, so yeah, I'm not super like I don't understand that so much, but it's some fancy math, I think. And I don't know why the Legendre thing is used here. I don't understand what its importance is. I don't know why.
I think it works out its relationship to the prime number, almost, and you can say it's either 1, -1, or 0, and then that puts you in a certain. If it's 1, do this, or if it's 0, it's obviously 0, and then if it's -1, it's not a square integer of the prime number. But I'm not too sure either.
It's not a square. So we're basically saying a not equal to p squared, like that. Is that this case, or is that this? Is it like that?
I think where we're returning 0, it's either. Yes, sorry, that's correct. Because it's saying it's not equal to 1, which means we're returning -1 or 0.
Oh, this is returning. Yeah, don't worry about this.
No, I'm not looking at that return. Yeah. So what I'm looking at is Legendre a comma p, what that returns. And if it returns a value other than 1, then it's either returning -1 or 0. And in those cases, I think it's not, a is not p squared.
Okay. Also,
we should look into this more over the next week. But yeah.
Yeah.
Some fancy maths. We can move on.
Yeah. Yeah. Anyway, so some fancy math is happening here. Yeah, actually, I'm keen to just have a bit more of a squiz into this, but yeah, let's leave it for now. So anyway, here, that's what's happening there, and the p is used. The p being the size of the field.
That prime.
Cool.
Oh, yeah, I see.
Yeah. Okay, so anyway, I don't even think that function is used, so that was a bit of a sidebar for us, but
it must be.
No. Let's see. Let's go from
what editor are you using?
Spacemax.
Oh, cool.
Yeah.
It's quite cool, but the lack of line numbers really confuses me.
Oh, I can add that space. How do I do line? Line numbers. Space TM, space T, space TM. Absolute. There you go.
Thank you so much.
I can put some CNN. Cool. So, all right, let's start going through this function. So the function takes in two lists of group elements. I know they're group elements just because they're called G, and I'm making an assumption because G is generally what is used
I made the same
code
one.
for. Yeah. So pretty sure those are group elements. So it takes in two sets of those. And in fact, the size, so we must make sure that the sizes of those arrays are the same as, these parameters which are set in the construction. And the one is actually set to 1 for now. It says something about a v2 there. So we know that num g2 is 1, and then the num g1 is going to be some other number.
Sorry, not the
this
number
thing over,
itself, though, the
yeah.
g2 dot length. So it's one number.
Oh yeah, sorry, my bad. Yeah, my bad. And over here, this unmarshal and marshal is just interpretation of bytes and then creating a number. So very simple, like from group element to bytes, basically. It's a serialization process or deserialization. Cool. Yeah. Alrighty, cool. So the inputs here must be the same length as what was set in the constructor. Then there's this thing. Now I don't remember seeing. Oh, I guess this is like how the randomness is created. Not super sure about that,
so
but we can dive into that.
Yeah. Okay. So what we're doing is we're taking an elliptical curve with the bytes of the two elements, or actually it's just G1, I think, with pi. And then we're taking the mod of that and the prime number, that big prime number on line 15. So we're calculating, I think, a point on an elliptical curve. I'm not too sure. But then we're finding that within the size of the field. So we're staying in the field. We hash randomness. So that'll be a hash function where the seed is probably this elliptical curve output. And then we typecast that to a uint.
Yeah. In fact, this thing has nothing to do with like it's not doing any stuff in the group or in the field. Oh, so now that I'm looking at this, I'm realizing I don't even know why there's this prime number over here. I kind of assumed that it was because of field stuff, but now I'm thinking actually it's not really. And the reason I think that is because this is just taking this is just a random number. Like I don't think there's any reason it needs to be part of a field. Like, I don't know, maybe it does. Maybe we see a bit later that inside of this function it does. But I think, yeah, like we can leave that up in the air for now. So over here, it's taking the group element and turning it into bytes. Yeah, this is the group. Yeah. Wait, sorry. Wait, maybe. Yeah, because over here we can see the type of this is the group element. Also, let's just go check out what that type looks like. It's just two numbers, and these two numbers have to live inside of the field. But that's just what a group element. That's how you can represent a group element. You can kind of think of it as the x and y coordinates on the Cartesian plane. Remember when we were having a look at the
those elliptical curves on the Cartesian plane. Yeah, and then you can just put that into a struct, which is nice.
Yeah. So this hash randomness, I was literally just doing catch-like 256 like on this data. So okay, fine. You know, we are taking. Whoops. Hello. What's happening? Okay, so we're just getting some randomness via both the running variable. So we see this is the thing that's updated at the end of the function. This is like the running powers of tau value. Whereas
I think it's in one of the papers, yeah.
Yeah, it was at the top here when they were explaining the. Here we go. So you basically keep this guy going, or is it? Yeah, because in order to get J, you need J minus 1. And there's this like recursive sort of definition or whatever. So if J is equal to 1, then you do that. Otherwise, you use the rolling, you use the previous one. So I think this element over here is, and that's not a power, that's not like, 2 squared or whatever. This is not powered like that. This is an index. I don't know why.
Okay, yeah, good distinction.
Yeah, it's very strange that they do that. But I was looking at these square brackets for a while. I was like, what on earth are they trying to say here? But I think, so this is like not g to the power of m, but it's just the nth g, I think. But I don't know why they don't put it on the bottom. Anyway, I'm a little bit confused as to this notation. But pretty sure that this is going to be an index over here because J is a person, J is an actor. And so this is the rolling G, and G being an element of the elliptic curve group. So that is this element that's being updated each time. And so we're finding some randomness by combining that and the G's and the pi. I don't know what pi, I don't know what this is, this pi. Maybe it's a prime number, maybe it's just some randomness. I'm not actually sure. We might discover a bit more about that later. Anyway, so find some randomness. Okay, and it's gonna verify some things there. I'm not sure about that. Let's get back to that later. Just pairing randomness. Okay, so more randomness generated. It's interesting that this is being done on the public chain.
That's probably why they do it so many times.
But everything is public then. Like, where's the secret?
Yeah, you can find out the Ketchak of the.
Yeah, so I don't understand how we can have this on a public blockchain. Like, the secrets are going to be public. All the inputs are public. Like, all these calculations are going to be public. I don't know. Interesting. I didn't think that would be possible, but maybe I'm missing something. Definitely I'm missing something, actually. All right, so let's go. Keep going. Got some randomness over here, which we can, whatever. I think I'm not sure how important it is that those particular elements are used, for the input to the randomness, but maybe we'll see that later when we go through the verification functions. Anyway, so now it's going to take this updated G1s, and so for each element in the G1s parameter, which is is it a single element? Oh, that's actually interesting. I wonder if it's a single. So G1s, is that a single group element or is that two group elements? It must be two, right? Oh, it must be multiple because this is an array. All right, fine, definitely multiple. Okay, so for each, yeah, okay, cool. So basically, this is containing a set of group elements. This is just doing the conversion, right? Just serializing them, or rather unserializing them into the types that we want. And then we have this updated G2. Oh, because there's only one element. So that second list of group elements is one big because of this restriction up there, remember? And this, okay, so this PI1, so that's another group element. All right, so this thing is not a prime number or something like we've possibly thought. It's actually another group element. So we have a bunch of group elements now. So we have a list over here, got one over here, and one over here. Now what are we going to do with all of those things? Okay, interesting. So there's just verification stuff here. Let's jump into those. Unless, do you wanna say something to you, or you want to go through something specifically?
In their repo, there's something called tech report. Just reading the .text, and it was verified or like edited by both Vitalik and Dan Bone. I don't know if you guys know him. He's my favorite cryptographer.
Yeah.
Also, Eli Ben Sasson looked at it. So I do believe that this is verifiable randomness, but I'm just trying to find where they speak about that randomness because it is on chain. So unless this is saying like, okay, because we know powers of tau is phase 1 and there is always a phase 2, maybe phase 2 must be done off chain.
Yeah, but then it's like, what is the point of even having the powers of
on chain?
Yeah, maybe, I don't know.
Yeah, it says, I know where you are now on update proofs. It's like the new parameters are well formed and the prover knows. I don't know, they don't mention the.
Will be quiet phone.
I might message some of the creators on Twitter and ask about this because I'm very intrigued. And then if I find out, I'll post a comment on the YouTube channel.
Cool, thank you.
But for now, there's no way of knowing.
Yeah. Update. Did you read that the proven knows section thing?
Yeah.
Okay. Knowledge soundness corrected. Alrighty.
Yeah. Sorry, but that was just my I'm hung up on this randomness now. But yeah, should we look at the verifiers next, or what were you thinking we should look at next?
I think we should go with verifiers. Okay, so verify discrete log. Maybe you should also quickly mention what discrete log means. Basically, the logarithm is when you're trying to find the power. So you have the base, you know the base, some number like 2, for example, and you know the result, but you don't know the power. So it's like 2 to the power of x is equal to 8. And log is going to give you x, right? Now, it's exactly the same in a group, except, well, this is actually the integers are a group themselves. And you'd rather say it's the same in a finite group, right? So I could have this be in a finite group, which is of size 11 or something. Or let me not say group, sorry, in a field. Yeah, so it's the same in a field, except computing the discrete log, computing the logarithm in real numbers and integers is not that difficult, but computing it inside of a finite field is incredibly difficult if the size of the field is huge, like it is in these cases. And
yeah, you need it to be huge here.
Yeah, and that's called the discrete log, because discrete just meaning it's not continuous. So I guess this would actually count as a discrete log, like if you're working in the integers. But if you're working in the real numbers, it's just called log. And in fact, a lot of cryptography hinges on the fact that this problem is very difficult to solve. And so that's where the word discrete log comes from. But let's see what it's doing inside. Okay, existing. So it takes the group, takes some stuff. Okay, let's see what it does. Left hand side, scalar multiply by existing G1. All right, I'm just going to put these so the existing G1 is what again? Okay, so that's like the rolling powers of tau number or whatever, the rolling group element. This one over here, updated. So the updated G1S. Weird, they only take.
But remember, because we have J and J minus 1, so it's possible that existing is when J is J, and then updated might be, or the other way around. So updated might be J, and then existing might be J minus 1, the previous rolling G element.
You mean like over here?
That's what I meant, yeah.
Yeah, I think this thing over here is definitely this guy, this previous G1. And then there's this stuff over here, which I'm guessing, is the input over here.
Okay, yeah, I agree with that.
And then this thing is just what we set it to. So this exact this exact thing over here, this assignment, I think, is exactly what's happening over here. But okay, I think that's what that is. So interesting. That just gets set to the first element of what? That is super weird. How is it? Okay, it's just being okay, maybe I'm starting to see now. I think all the calculation and stuff has to be done off chain, and this whole thing is actually just a verifier, I think, because like no calculation is being done. Well, there's verification calculation.
Yes, okay, absolutely. I agree.
This is directly coming from the parameter, right? Like
so you're passing that in. Yeah.
It's just being unserialized, and then it's being set.
Because also in other stuff I've seen, like you create the proof in SOCOM and you only do the verification, the validation in Solidity and on chain. That makes sense. Like all you can do is verify on chain, because on chain you can have true randomness.
Yeah, I think it's just it's a little bit like offsetting, or like of a misnomer that these things, for me anyway, maybe I'm sure we'll understand it better in a bit, but like why it says randomness over here, it's literally taking the hash of some stuff. So I was like, is that where the randomness? Yeah, it's like, I don't know. So anyway, that I think we'll find out soon why these things are here. And it's also using check, right? Like, nowhere in the paper was it like, oh, we use the catch-up hash function. Like, I don't see any. Well, look, not that I read this whole thing, but I didn't see any mention of a hash function here. So that's why I was assuming
true.
that the hash function's role in this particular piece of code was to create the randomness, but to do the computation. But that can't be the case because the computation must have been done off-chain. Anyway, let's go with this verification and see what it does. Okay, so let me maybe do that. Yeah. Okay. So we're going to multiply the existing G1 by PI2. What? That's interesting because I thought PI2. PI2. Oh, okay. Sorry, I'm getting confused between PI1 and PI2. So PI2 is set to what? Yeah, where's that thing set? That wasn't oh, it is. Oh, you sneaky little. I didn't see that extra parameter. My bad. There's not 3 parameters, there's 4. So yeah. Okay.
I also didn't notice it because it's on line 41 with the public.
Yeah, it's hiding over there. Sneaky little parameter. Okay. So scalar multiplication. I think in this case, think like a group element is not a number. So, you can't say if we had 2 numbers multiplied together, they'd create another number. But with these group elements, if you multiply one by a number, that actually doesn't mean anything. Yeah, you get technically it's not.
No, I mean, sorry, if you multiply the 2 elements, you get a new element. But if you multiply one by a number, it just changes that element, surely, but it's not making a number.
Yeah, so it's not actually defined, it's shorthand. So you can't multiply a group element by a number. It's just like a quick way of writing that element added to itself a few times. And also when I say add addition.
That number many times.
Yeah, exactly. But also addition
it's not straight addition. You explained earlier it's addition with a modulo of a prime number.
Oh no, that's in the field. That's in the field, but in the group it's very different. In the group it's different because the elements are not numbers. So how could I use regular addition or addition modulo if I'm not working with the numbers? So basically when they say this, maybe do you think we should quickly do no, actually no, that's going to be too far down a different rabbit hole.
Unfortunately we're coming up on time.
Oh, for real?
So we can't go down that rabbit hole, but perhaps cool. in a part 2.
Yeah. Anyway, so this is basically just saying the group element added to itself, addition being the special operation in that group, a number of times. How many times? PI2 times. So PI2 has to be an integer. There's no meaning of adding some group element to itself 1.5 times.
Yes, and it also has to be a uint. You can't have a negative number.
Yeah, exactly. Okay, cool. So that's what we got there, and we have the same thing over here. Oh, randomness FR. Okay, that thing is the discrete log randomness. Okay, cool.
FR stands for real.
Interesting. Lol. FR is that prime number that's defined at the top of the thingy, remember? But yeah, I'm pretty sure they meant it to stand for real.
Must have, yeah.
Okay, cool. So we have this. Okay, fine. So we add these group elements to each other, and then we add. .g1 add. Not and this one. Oh, that's not a group element. Okay, cool. So basically, what we're saying, if I could just write just a little equation here, it's like a g plus b. Maybe let me just use some times here. AG prev plus BG now current one, and that wait, is that true? What do we do with the left hand side? Where is? Oh, okay, never mind. No, that's rubbish. This is not the case. It's that thing. And then multiplied by, I don't know, I'm just going to call this pi, or let me call it little g. Okay, so this thing, oh, it's a plus there as well. That is what those 3 lines are doing, is creating A, which is pi2, times by the previous group element, plus little g, which is this pi1. And that pi1 is a parameter from the previous function. Cool. And then we're verifying that that thing, I think, is equal to that. Is that what we had? Left-hand side dot x is equal to right-hand side. And this thing is left-hand side. Yeah, this is exactly what we're doing. So it's checking that this equation holds. The x and the y are just the 2 elements of the group, the 2 numbers that define the group element, or that you can use to write down the group element. Okay, cool. So we're getting somewhere with this. We've seen that is what this particular verification is doing. Let's quickly go on to the next one, verified pairing. Pairing is actually type of function that's used on the ZK snarks. It's a function from the Cartesian product of one group, which I think is the elliptic curve group, to some other group, and I'm not too sure if that's an elliptic curve group. Anyway, it's like some math thing. That's why the word pairing is there. And let's see, this math looks a little bit more intense. Okay, RHO. So some hash things. Here we've got this one, R, which is the input group element. Rolling row. That's nice to say, rolling row.
Yeah.
So now this is using all the group elements that were given in the parameter. Mod. Hello. Where did you come from?
Stent, how much is left of this contract? It might be worth doing a part 2. And
it's literally just these verification things.
Okay,
so
cool.
maybe not worth doing a part 2 for this particular one. I mean, look, also it's going to take us a while to figure out what the F is happening here, and then we're going to be like, okay, fine, we figured out the equation, but now what? So I think it would take a bunch of time. I could be keen to keep going at some point with this particular piece of code. Yeah, if you think that's a good idea, I'm in. But maybe to round off, we just say like this is definitely just verifying some group some group multiplications and additions and whatever. And I think the important thing is it's difficult to figure out the group element that makes this correct. So I think that's the difficult thing that was figured out off chain. And then it's just done on, the verification is done here. But I'm still confused about the randomness factor and how that's checked. Yeah. Is there anything else you wanted to say or go through?
Nothing comes to mind. I think we're right. I'm glad we realized that some of this is done off chain and just verified on chain. And
Yeah.
we feel a lot more secure in it. I'll definitely read that paper that they published, that tech report. And yeah, thanks. This has been really interesting. Yeah, is there anything else you want to add?
No, that's it. Just thank you for having me. And it was good to go through this code with you.
Yeah, thanks. It's always so fun to have you. Hopefully have you for another Zero Knowledge repo. And thanks everyone for watching another episode of Solidity Fridays. I will catch you next Friday. This has been another episode brought to you by Linum Labs.